so we have discussed this adjoint for explicit operations. That's quite useful for a number of things. So naturally, that leads to what if I have an unsteady PDE? So it turns out that I can generalize this formula to actually, let's first say discuss ODEs, right? For PDEs, it's a little bit similar. So for example, this is the adjoint field of unsteady flow over a circular cylinder. So so basically the flow goes in this direction, and the black contours outlines the wake of this cylinder. And what you see is the adjoint field. It seems to be it's an unsteady field that seems to be propagating, generated from the cylinder and propagates forward. It propagates actually upstream towards the left. And we're going to be studying how to interpret, how do we derive the adjoint for unsteady differential equation, and how do we interpret them. Okay, so here let's actually only start with an ODE. So what if I have an optimization problem, minimize J as a function of U and S, subject to du dt is equal to f of U and S. So this can be a semi-discretized PDE. So if you have a PDE, you can discretize it with finite difference, finite volume, or finite element. You're going to get an ODE, right? And my objective function, for example, in this example, is the time averaged drag on the cylinder. You may also have other objective functions that are defined on as a function of this solution. And let's start by considering a particular form of J. So J is equal to, has two components. One is a time integration of, let's write it as a small j of U at time t and S dt, plus another term that depends on just the terminal condition, J, let's say Jt of U at time t and S. So this is this covers actually a lot of cases. So the first term is if you are interested in a time integral of something or time average of some quantity. The second term is interesting if your objective function depends on what is the end state of the evolution, right? So actually one of the first applications of computers, I mean, the first electronic computer is actually founded by the Navy. They want to do calculations of trajectory of guns, like if they shoot out a gun, like where they end up, right? So so if you do optimization to this problem, so for example, if you want a shell to fall on a particular location, and you want to optimize what should the initial angle of my trajectory be. So the S is going to be your initial angle. The J actually now depends on the terminal condition, right? It depends on where the shell is at the end of the time evolution. So that'll be the second term being important. Okay, so for that objective function, let's use the same method, the Lagrange multipliers. As opposed to the previous discrete case, we now have an infinite dimensional Lagrange multiplier, because this equation needs to be satisfied for all the t within the time interval 0 and t, right? And also we assume we have a fixed initial condition. Okay, so that's given. So if these equations are satisfied for any t, then when we look at this equation, du dt minus Before we introduce the Lagrange multipliers, let's actually linearize things first, right? So actually, you can do the Lagrange multiplier then linearize, or you can linearize then do the Lagrange multiplier. So let's actually try the first case. So we want to introduce a Lagrange multiplier. Let's say u hat, and u hat now is also a function of t, because I'm transposing u hat and multiplying u hat with this differential equation du dt minus f, right? And so because this is true for any t, I can introduce a u hat of t not being a fixed value, but being also an arbitrary function of t, and the product would still be zero, a zero function of t, right? Okay, so the equivalence of doing the inner product in the continuous sense is to multiply and then integrate. So that gives us a modified objective function, the original objective function plus a bunch of plus essentially zero. When the constraint is satisfied, this is still true, okay? And then the next step is to linearize. So as I said, you can linearize, then then add the Lagrange multiplier, or do the other way. So once you linearize, my delta j is going to be integral of partial j partial u times delta u. Let me just skip the s for now. You can imagine if I have this s, it's just the two additional terms in the objective function, right? It doesn't really. You just need to carry them every step of this derivation. Plus partial jt partial u times delta u at t. Okay. And then this term is going to be linearized to u hat is going to stay the same, d delta u dt minus partial f partial u delta u minus partial f partial s times delta s. Okay, again the objective is to eliminate all the appearance of delta u's. So how do I do that? And there is an additional challenge here, is that delta u's doesn't just appear in ordinary terms of this equation. It also appears in a derivative. How do we deal with that? We need to kind of combine all the terms that has delta u's, right, and figure out what u hat is to eliminate these combined terms. But how do we combine things when delta u is inside a time derivative? Do you know any manipulations that can pull it out of the time derivative? Integration by parts, right? So that's a very commonly used technique in deriving the adjoint. That is integration by parts. If you have any of these deltas you want to eliminate that lives inside differential operators, use integration by parts to pull it out. If it lives deep within differential operators, let's say in the second derivative, then use integration by parts twice. If it's in the third derivative, use integration by parts 3 times. Okay, so integration by parts. So this term, let's actually just look at this term. This term is going to be, let's just look at this term. This term is going to be, first I have a boundary term, u hat of t, delta u at 0 and at t. At 0, we already know if u0 is fixed, delta u0 is 0, right? So we don't care. We only care about at time t. Oh, all right. And then the remaining part is still an integral, but the derivative, but one is you get a negative sign, and another is the derivative now applies onto this, right? So I can also say we have d u hat transpose dt times delta u. So that's the effect of integration by parts.